Our next speaker is Dr. Liz Borowsky, a Senior Director of Engineering at Akamai Technologies. As head of Akamai's mapping department, she is in charge of the brains of Akamai's network. Her team runs the software that directs traffic to Akamai's worldwide distributed network, routing roughly 25% of all internet traffic daily. Wow. Dr. Borowsky started her career in mathematics with an undergraduate degree in mathematics from Williams College and a PhD in theoretical computer science from UCLA. She has worked in industrial research, academia, and industry. Throughout her career, the common thread tying these roles together has been a focus on problems of optimization and coordination in distributed systems. She loves thinking about how pieces of a system in different parts of the world with different characteristics can be made to work together. Dr. Borowsky brings her love of worldwide system integration to Akamai Technologies, the leading global service provider for accelerating content and business processes online. Today, Liz is here on behalf of Akamai and the Akamai Foundation. The Foundation's mission is to promote excellence and innovation in math. It's a major sponsor of many wonderful mathematical opportunities for young women and men, including the USA Math Olympiad and the Math Olympiad Summer Program. Akamai is also a major sponsor of the U.S. teams to the China Girls Math Olympiad. And we are deeply grateful to Akamai Foundation for its support of the Advantage Testing Foundation Math Prize for Girls. Please join me in welcoming Dr. Liz Borowsky.
Hi. First, I want to say, wow, look at all these math girls. This is awesome. Thank you for inviting me. It's an honor to be here on behalf of Akamai and the Akamai Foundation. For those of you who don't know what Akamai does, as you were just told, we're a content delivery network. We have machines, computers, in, I think it's about 85 countries now. All over the world, and we deliver a quarter to a third of all internet traffic daily. So most of you use Akamai every day without knowing that you're using it. For example, if you go and post on your favorite social networking site today about what an awesome time you had at the Math Prize for Girls, you're probably using Akamai. If you looked for your travel reservations, or your maps for how to get around Boston, or what to do this evening on the computer, you're probably using Akamai. Our goal is to make the internet basically work. So we want to make it fast, we want to make it reliable, we want to make it something that you just don't even think about, that you have at your fingertips, it's there, and you don't even need to know that it's, how it works or what's going on, that it's essentially a utility. And you know what? That goal is working. So if you had told me when I was your age that there was going to be an internet, that I was going to, you would have data at your fingertips anytime you needed it, that you could send pictures willy-nilly all over the world, I might have believed you. If you had told me that I would be at the core of it, making that work for people and directing a whole bunch of other engineers, I wouldn't have believed that. So just open your mind to anything can happen. What I wanted to tell you is that mathematics is really what made both sides of that equation happen. So Akamai was founded out of an idea hatched between Professor Tom Layton, who's a professor at MIT here. He's now the CEO of Akamai, but he was one of the founders, and his grad student. The internet was new. And they had this idea of what if you hosted that data closer to the end users so that the time it took to download things didn't take so long. At the core of Akamai's technology, we use math principles every day. We do optimization. We use mathematical models. We measure the internet constantly, all the time, and we use statistics and modeling to interpret that data and make things run smoothly. At the core of everything is math. For me personally, Mathematics was what got me into computer science in the first place. So I loved math in high school. I was one of 2 girls in my AP calculus class. My teacher at the time had all ends of fun pointing that out to the boys because the 2 of us broke the curve, and he made good fun of all the guys in the class. So I went to college. I didn't know what I wanted to do. I liked math. I was pretty good at it, so I continued on in it. And as a math major, they made me take a computer science class. And I had no interest in computers at the time. Computers, who needs them? What are they good for? I didn't know. But I even asked them if I could take, the little computer science class that was a 1-semester thing, would track you out of it. They said, no, you're a math major, you can handle it, take the regular class. So I did. I took the computer science class in my sophomore year, and I found that it was really fun. You got to build things, and it was concrete. It used all the same logic and principles that you all know and love, or you wouldn't be here. And yet, at the end of the day, you built something that worked, and that was really cool. So when I finished undergrad, I went to grad school in computer science because the math I loved most was sort of on that boundary. And I was rather intimidated for being there because I was meeting all these people, mostly men, well, totally men, who had been playing with computers and circuits and programming since they were probably, 4 years old and could talk about bits and bytes in this old computer and that old computer. And I had just recently taken my first class in it. But after about 2 years of being in grad school, it took me a little while, I was a little slow on this one, I realized that my math background was so much better, prepared me so much better for the work I was doing than all that computer science that my colleagues had taken. It's fairly easy to pick up a computer language or a concept or, learn a new operating system. It is not so easy to pick up, linear algebra or algebraic topology. And those are the things, those foundations that help you solve the problems and structure the way you think. And so for you guys who are in math now, whether it's what you pursue for your life or whether it's a stepping stone on the way to other disciplines that you love, this foundation will give you the background you need. And it will be beneficial to you for anything you do. Be it art, be it engineering, be it science, all of these things, anything you do, that structured way of thinking and approaching problems and being precise will benefit you. So at this stage, some of you know what you want to do, others of you have no idea, and that's okay. So my advice to you, based on my own experience, is just keep an open mind. Try anything. Trust in yourself and your ideas. If you think it's important, then it is. Other people will think it's important too. Trust in yourself, and if you can't, if you don't have that confidence, fake it. Nobody will know the difference, and you'll find that you can do it anyway. I figured this out in grad school. I was like, well, if I were a guy, I wouldn't have a doubt I could just do this. So I pretended, and you know what? I could. It was pretty cool. Know that in your lifetime, the world will change in fundamental ways that you cannot predict now. And know that it's more fun if you're making those changes as opposed to watching them. So dig in, jump in, have fun, and just follow your dreams. Thanks very much, and good luck, everyone, this afternoon.